Morning and welcome to another Chai and Bye. So recently we all celebrated Diwali and we are starting Nobel Chai and Bye series with a talk on quantum thought for which Nobel Prize for Chemistry was awarded this year. So today's speaker is Ms. Payal. She is a research scholar in Department of Chemical Sciences at CIFR, and she will tell us about what is this all, what is it that got a Nobel Prize for this. And I may add one more thing that this talk as an experiment is going to be primarily in Hindi, but you are welcome to ask in English as well. And maybe people can come slightly in front. That will help. Okay. So, all right, all yours, Pai.
So hello everyone. Today we have gathered here for the fantastic work done by these three great scientists. These three great scientists for the discovery and the synthesis of quantum dots. And this year they got Nobel Prize for these quantum dots. So in my upcoming slides, I will tell what was so special about these quantum dots and what were their efforts to discover and synthesize these quantum dots. So to begin with, we know that everything we see around us is made up of atoms, and each atom constitutes nucleus and electrons around it. But everything we see is of different color, different properties. So, but the constituent is nucleus and electrons. So what is that is giving different properties to these materials. So it is the electronic distribution and the number of electrons which decides the properties like melting points, boiling point, and color. So for now, we will focus on color. So what could be the reason of a color in a material? So for that, we have to first understand what is band gap. So if we take a atom, then it has electrons. They will stay. They have house to live in atom. That is called energy level. And when we take more and more number of atoms, then there are more and more energy levels, but still they are discrete. But when there are infinite number of atoms, like Avogadro number 10 to the power 23 or higher, then these energy levels will no longer be discrete. They will appear as bands. And the difference in energy between these bands is known as band gap. Lower band is valence band and higher band is conduction band. And depending on the value of band gap, metal, semiconductor, and insulators are classified. So the materials which have zero band gap are known as metals, and in case of semiconductors, the band gap is such that it can absorb the visible light. And in case of insulators, this band gap is higher than semiconductors. So now, today's Nobel Prize is all about semiconductors. So now you know about band gap. So why any material has a color like as it is? For example, you can see here mug. Why it is looking like red in color? So whenever light falls on any material, all electrons in the band get excited, and when they come back, depending on the band gap, they release energy, and each energy has particular wavelength, and depending on the wavelength, they have different colors, so they appear as color like that. For example, if there is less band gap, then the material will look red in color, and as the band gap energy increases, then the color of material moves towards bluer side. So now you know that band gap decides color. So again, we take this mug, and if we want to take smaller version of this mug, then again also it will look red because band gap is same. Now further we reduce the size of cup, then also it will look red in color because band gap is same. Now see this. This is glass, and this is same glass. Now in different regions, it is showing different colors. How this can be possible? Just now we see that if we take smaller version of any material, then it will have same color. But this this is whole glass, but at different regions, it is showing different colors. How this can be possible? So this, uh, I tell you about the history of these glass. These glass were made by glass makers in ancient times. So they used to make glass by taking metal inside glass melt, and depend they used to heat these glass to make this glass. So same question, that why this glass is giving different colors, aroused in the mind of this person, that is Yekimov, in 1979. So when this question arrived in the mind of Yakimov, what he did, he went back to his lab, and he tried to make those glasses by taking copper as a metal and chlorine and glass, and heated that glass at different temperatures. And what he saw is that when he heated this same melt at different temperatures, depending on different temperatures, he was able to see different copper chloride crystals in the glass. So what was happening? So he observed that thus when he was heating those glasses at different temperatures, then different colors was arising. And this was so interesting because this was happening at nanoscale, not in micron scale or the objects you can see, but it was the copper chloride crystals were in nanoscale. So if you don't know about nanometer scale, then I tell you, if you consider a earth and a football, for a football, the earth is so much bigger in size. For that, any atom, we consider football and atom, they will have same size difference. So nanometer is roughly around 10 atom size. Okay, now you can get idea. So so now the properties which were the color which was same in bulk level, now in nanometer scale the color was changing, because when we go to nanometer scale, then the band gap was changing. So from now we conclude that when the object is in micron scale or higher, then the band gap remains same and color is same. But when we go to nano scale, roughly around 10 atom size or higher, then the band gap does not remain, band gap energy does not remain same. It changes with size, and this phenomena of change of band gap is known as quantum confinement. So now, in how many directions a material should be smaller to show this quantum confinement? So for example, we take a 3D bulk material, and if we cut it like a cheese of slice, means we have made it smaller in one direction. So now also we will see quantum confinement, but the amount of quantum confinement effect will be less. If we further reduce this series of slice into further like quantum wire size, then the quantum confinement effect will be even higher. And if we further cut this into further pieces like as shown in 0D quantum dot, then the quantum confinement effect will be higher. So this is known as quantum dot, where the quantum confinement effect is higher. So now Ekimov understood all this, then he published his publication on this quantum size effect in 1981. Now quantum dot was embedded in glass, but for applications we want the quantum dots to come into solution. So there came second scientist Brus in 1982, where he was able to take these quantum dots into solution. He could make the colloidal solution of these quantum dots. Now, what can be the problem? What can be the problem of bringing quantum dots in colloidal solution? Consider a particle of quantum dot, then another particle of quantum dot will try to come together to that quantum dot, and they will try to become bigger and bigger particles. So this was the problem of making quantum dots. So what Brus did, yes, yes, okay. So what he did is that, yes, yes. As I said that the copper was in glass melt. So now the copper chloride crystals were embedded in glass slide. They were not free in solution. Yes. Copper chloride crystal he was making. Yes. Copper and yes. He was taking copper, chlorine and chlorine gas. Yes. He was passing to the yes. And he was heating at different temperature. Yes. But they were embedded in glass, they were not free in solution. What? Yes. It was, if you consider a watermelon, they have seeds on it. Like that, copper crystals were there in glass. Yes. No, they had no control of size. Yes. Yes. So then came Brus in 1982. So as I said that Yekimov, what did he was embedded, that was embedded in glass. But now he wanted to bring those quantum dots in solution. So that was difficult, as I told. So what he did is that he capped those quantum dots with some capping agent, and they did not allow two quantum dots to come together and make bigger particles. So now he was able to control over size of quantum dots. So for this he published his paper and he made colloidal CDS quantum dots in 1984. So then in case of Brus, the limitation was that he could synthesize only one size quantum dot, and then also the synthesis was not that so much easy. So then came Bawendi. Yes, these two scientists were working independently. They didn't know about each other. They were doing everything in their particular place, and they didn't know that other person is also doing that work. So then independently, Bawendi was also working on these quantum dots. What he did, he beautifully created a synthesis of these quantum dots where just by heating you can change the size of quantum dots. And this method was so easy that you can easily make scalable quantum dots. Means in large amounts you can make these quantum dots. So the benefit of this scalable synthesis and easy synthesis was that everybody can make easily in their lab these quantum dots, and we can bring these quantum dots into applications. So now, are you interested in seeing these quantum dots? We in our TIFR also we have made these quantum dots. Are you interested? Okay, so these quantum dots are of same material, but they are of different colors. Now you will see, we will shine light on these quantum dots. So they have just difference in size. They are just are of same material, cadmium telluride quantum dots. So if
so you have some light.
Yes, so we have brought some light source UV lamp. So first I take one size particles of one size quantum dots, and if we see like without light, we cannot see the shining in quantum dots. Then if we bring in presence of UV light, you can see the fluorescence. Other size quantum dots, they are of different colors. You can see the color. Are you able to see? Okay.
So after the online talk, we can some close and
Okay, so the synthesis was so easy that now everybody in lab can make easily these quantum dots. So after the discovery and the easy synthesis of quantum dots, now these quantum dots started coming in various applications. So I will be discussing some of those applications of quantum dots. So one of the application is biological application. So everybody must have suffered from any disease. Everybody in some time in their life, they have suffered from any disease. So what you do? You take a drug for curing that disease. I think slide is, pointer is not working. Not working. Okay. So you are suffering from any disease, then what you do is that you take a drug to get rid of that disease. Then drug don't know that in what region it has to go to protect. Means it you have taken a medicine and you have headache, suppose, but drug does not know that it has to go to cure disease in there is something in your head or somewhere where it has to go. So in drug there is a targeting vector which tells direction to drug that it has to go in that region only. So there is a targeting vector, and if we want to see that these drug and targeting vectors have reached to the desired disease, there is a reporting unit which tells that drug has reached to the disease area. So, for example, we see here schematic of a drug. So it has a reporting unit, and there is a targeting vector and drug attached to it, and there is a tumor. Then when it goes to tumor, so now it will give fluorescence. It will give some color. For example, here it is giving sky blue color. Okay. So now if we see a mouse, if we want to, if it has cancer and we don't know where in what region of the body it has cancer, so what we do is that we label different parts of body with different dyes, and then we send our drugs which was of sky blue color, and if we see sky blue color with green color, then means this green color portion has cancer in mind. So by this means we can see where cancer is in our body. So now if we want to use this scheme, then we have to have a dye which has of different colors. So this can be easily done with the help of quantum dots. We don't have to go by a lot of synthetic schemes. Just by changing the size, we can create these different color dyes and easily detect simultaneously where the cancer lies. So this is we get with quantum dots. Then you must have gone for shopping, where you must have seen that the person is scanning the barcodes, or you have must use the QR codes. So these QR codes have made life easy by easily you can get information of any product. So now if you want to put those barcodes or barcodes in a very miniature size object, then what you will do? These are very big size. So then you can make barcodes of quantum dots, like as shown in figure. This is a quantum dot barcode. These are of nanometer size scale. scale size. So you can easily put these barcodes on that object which is very small in size, like in nanometer range. So then another, you must have seen LEDs, and now another technology is coming which is using quantum dots in LEDs. So in conventional LEDs, what was the problem is that they they were using colors, they were emitting out colors which were mixing with each other, and the colors were not bright. But now in quantum dots, as I said, they are just 10 atom size, roughly around 10 atoms. So they have discrete energy levels, and the emissions come out from them is very sharp, and there is no mixing of colors like as shown in right side, and hence since there is no mixing of colors, then the color appearing from them is very bright. Also, there is a photovoltaic application. So you must have seen somewhere solar cells. There also outside I saw a solar cell outside this campus. So what is the use of solar cell is that we take sunlight energy and convert that energy into electricity. So this problem is not easy because we want more and more sunlight to capture and convert electricity. Then only it can exist here. So for that, we need a material which can easily capture all those sunlight and convert into energy. That is possible if the band gap is such that it can capture most of the energy. And this is available in quantum dots. We can easily tune the band gap in case of quantum dots to fulfill our requirement so that it can take more and more energy from sunlight and convert into electricity. So, hence it can be used in photovoltaic applications also. There are many other applications. For now, we can read more and more applications where these quantum dots are. And for now, we will stop here. Thanks for the patience of listening. If anybody has question, you can ask.
Well, you really read through the session. Typically, the session is much longer, and he has apparently just raced through the. So there is not small question online. It's about why do they
So in case of nanoscale, what happens is that with the change in size, the band gap difference becomes changes with the size, change of size of object of quantum dot. So since band gap changes at quantum scale, then the correspondingly different color comes corresponding to that band gap. Okay, anybody has any questions, you can ask. Okay, the capping was done with the help of a capping agent TOPO, which is a ligand which surrounds the quantum dot, and another quantum dot also has same capping ligand, and this does not allow these quantum dots to come together, and hence they cannot aggregate. So this allows the size to be maintained as whatever it is in nanometers. So anybody has, if anyone wants to see these quantum dots of different size, can come here and see in